In example 6 from note 6.7, we're going to look at electricity. It's another example of simple harmonic motion. I'll read the top paragraph. The electricity supply to your house is called alternating current, AC, because the current varies sinusoidally with time. The voltage that causes the current to flow also varies sinusoidally with time. Both the current and voltage have a frequency of 60 cycles per second. So frequency is the reciprocal of the period. But they can have different phase displacements, though, which we would call horizontal shifts, depending upon the elements in the circuit. For example, resistors, capacitors, and inductors. Figure 1 shows a diagram of the current and voltage in a circuit with just a resistor and some kind of generator for the current. So I is the symbol that's used for current, and V is the symbol that we're going to use for voltage. So in a circuit with only a resistor and an AC generator, there is no phase shift because the current I and the voltage V as functions of time they coincide. In figure 2 now, we have a circuit that has a capacitor and an AC generator. With this, the introduction of the capacitor causes a phase shift. So I'll read the paragraph. In an AC circuit consisting of a capacitor and an AC generator, the current I and voltage V are not in phase as they were for the circuit of a resistor and an AC generator. The voltage reaches its maximum value 1/4 of a cycle after the current reaches its maximum value. Thus, the voltage lags the current through the capacitor by 1/4 of a period. And we can see that on our diagram, right? The voltage is peaking as the current crosses the axis of oscillation. So it's 1/4 period behind. Okay, so letter A, after that intro, says, suppose that the current is at a maximum, IM, is 10 amperes. A stands for amperes. When t equals 0, or 0 seconds. Find a particular equation for the sinusoid showing the current in figure 2. Remember, AC current has a frequency of 60 cycles per second. Okay, so we need to write the equation. So we know that the amplitude is equal to 10. So that's our A value. We know that the period is 1/60th of a second. If there are 60 cycles per second, then one cycle takes 1/60th of a second. So that's the period. So now we can find B. So the period, 1/60 is equal to 2 pi over B. Now we can, cross multiply. So B is equal to 120 pi. So that's our value for B. So we know A and B. And now we want to write the equation. Oh, the axis of oscillation is at y equals 0. So in this case, it's actually I equals 0. So there's no vertical shift. So we're ready to write the equation. So I'll scroll up and look at the graph. So we're writing the equation for the current. So the current equation is at a maximum. So starts at a maximum when t equals 0. So I would like to use cosine. So cosine has no horizontal shift and it's not reflected because we're starting at a maximum. So we're ready to write the equation. So we can say I of t, the current as a function of time, is equal to 10, the amplitude, times cosine of B, which is 120 pi t. Okay, letter B says, as shown in figure 2, the voltage lags the current by 1/4 of a cycle. By how many seconds does the voltage lag the current? So that's going to be 1/4 of a period. And we said that the period was 1/60th of a second. So it's going to lag the current by 1/240th of a second. And if you get a decimal approximation, that's about 0.00416 repeating seconds. Letter C says if the peak voltage, Vm, is 180 volts, Find a particular equation for voltage as a function of time. Okay, so now we have the graph here. We're going to be focusing on the voltage equation. So we'll look at the voltage graph. So for this function, we know that the amplitude, A, is equal to 180. That's the maximum voltage. So this is 180. And there is no vertical shift. So D equals 0, or the axis of oscillation is at V equals 0. And then the period, we calculated the period in the previous example. So that's 1/60th of a second. And we know that that's equal to 2 pi over B. So if we solve this like we did before, B is going to be equal to 120 pi, the same thing we found in letter A. So we know A is 180, B is 120, D is equal to, B is 120 pi, and D is 0. So when looking at this graph, we can choose whether we want to use sine or cosine. Since this graph crosses through the midline going up, I would use sine. It has no horizontal shift, and it has no reflection in the x-axis because it is going up through that midline point. So we're ready to write the voltage equation. So V of t is the amplitude, 180, sine. B was 120 pi, so 120 pi t, and D is 0. So we don't need to write that. That's an equation for the voltage. Letter D says, what is the voltage at the time the current is a minimum? So let's take a look at this graph. The current is a minimum when the voltage has gone through half a cycle, right? They lag by 1/4 period. So I'll write that down. So when the current is a minimum, voltage is 0. We could check this with our equation if we wanted to. We know that the current is a minimum after 1/2 of a cycle, or 1/2 of a period. We know that because the current started at a maximum, so a half a cycle later it'll be at a minimum. So that's after 1/2 times 1/60th, so that's 1 over 120 seconds. And we could substitute that into our voltage equation that we found in letter C. So we can find V of 1 over 120, and that's going to be 180 times the sine of 120 pi times 1 over 120. The 120s cancel, so this is 180 sine of pi. And if we think back about our unit circle and where pi lies, pi is there on our unit circle. So the sine of pi is 0. So the voltage after when the current is at a minimum is 0 volts. For letter E, we're going to solve an equation, the trigonometric equation. So it says, what is the first positive value of time at which the voltage reaches 170 volts? So here we need to solve the equation. When is 170 equal to 180 sine of 120 pi t? And that's our voltage equation that we found up above in letter C. So to solve this equation, first we want to isolate sine. So I will divide by 180, both sides. So now we'll get 17/18, I'll cancel out the tens, equals sine of 120 pi t. To undo sine, we're going to use inverse sine. So sine inverse of 17/18 is equal to 120 pi t. If you plug that into your calculator, I'll divide by 120 pi first before I plug it in. So I have 1 over 120 pi times sine inverse of 17/18. That's equal to t. And if you plug all that into your calculator, you'll get 0.00327 seconds.